section 5.1, we are going to talk about polynomial functions and models. I'm using a different type of screen recorder, so I can't exactly see what's in frame and what's not in frame. So if things go weird, I apologize in advance. So let's talk about first what polynomial functions are and what they are not. So a polynomial function is a function that has whole number exponents on the variables. So what can it not be? Well, what can it be? Yeah. So like x squared, or x to the first, or even x to the 0, which would be 1. So all of those things are polynomial functions. What it cannot be is things like x to the 1/2, which is square root of x. It cannot have negative exponents, which would be like 1 over x squared. So since it can't have negative exponents, you can't have variables in the denominator. And since it can't have fractional exponents, you can't have variables in the radicals. So right there, these are our two big domain restrictions. So since we can't have either of those things, polynomial functions are really nice because they don't have domain restrictions. We also can't have exponents that are like radicals. So they have to be whole numbers. They can't be integers. They can't be rational numbers. They can't be irrational numbers. So here's an example of a polynomial function. And we want to talk about the leading term, the leading coefficient, the degree, and the constant term. The leading term is the term with the highest degree. Now, in the function that I've given you here, it's in what we call standard form, which means that it goes from highest degree to lowest degree on the exponent. So if your polynomial function is in standard form, the leading term will be the first term, but it's not always. In this case, it is. So this one right here is our leading term. So 3x to the 5th. In general, it's the term with the highest degree. The leading coefficient is the coefficient that's on the leading term. So right here, 3 is our leading coefficient, and it is the coefficient of the leading term. Remember, leading term doesn't necessarily mean the first term. It is the term with the highest degree. The degree of the polynomial is the degree of the leading term, or the highest degree in the polynomial. And the constant term is the term that does not have a variable on it, where actually the degree is 0, since we had seen here that x to the 0 is 1. So technically, is there an x here? Sure, and it's to the 0 power. So this guy right here is our constant term. It's 83 in this problem, and it is the term without a variable, or with a variable to the 0 power. The degree of a polynomial tells us some important information. So in this example, our degree was 5. The degree of that polynomial, they usually call that the letter n, lowercase n. It tells you that there are at most n real roots, which we also call zeros and x-intercepts. All of those things will be interchangeable. So when you're asked to find roots or x-intercepts or zeros, those are all the same thing. Then there would be exactly n complex roots. So complex roots include imaginary numbers And you won't see them on the graph because when we graph, we are graphing in the real numbers. So if it's not a real root, you won't see it. And then there are at most n minus 1 terms, which we call like maxes and mins. So think about in terms of a parabola. A parabola would be degree 2. Let's see if I have a parabola here. The most number of roots I can have is 2, 1, 2. But I could have 1. We'll pretend that crossed or touched. Or I could have 0. Then there are exactly n complex roots. So technically this guy has 2 roots, but they're the same one repeated. This one has no real roots, so it's going to have 2 complex roots. And then terns, which are maxes and mins, this is degree 2. And we can see that we have 1 tern, 1 max or min in each one. 1 tern. So on a degree 5, I would say that there are at most 5 real roots. There are exactly 5 complex roots, and this polynomial can have at most 4 terms. So it could go, there's 1 tern, 2 terns, 3 terns, 4 terns. 1, 2, 3, 4. But it doesn't have to have that many. Graphs of polynomial functions. They are nice. They are continuous. Continuous means, for lack of like a math description, if we just wanted to describe it in general words, that you can trace your pencil from one end to the other without picking it up. So think of a parabola. We can go from the left tail to the right tail without picking up our pencil. Think of y equals x cubed. Same thing. That's that squiggle graph. Think of y equals 1 over x. That's the rational function. It's not a polynomial, and we have to pick up our pencil to go, it's the one that goes swoop, swoop. You have to pick up your pencil and start again. So what does that technically mean? It means there are no jumps, no holes, no vertical asymptotes. So they are continuous and they are smooth. So in this case, smooth means there are no sharp turns or corners. Sharp turns are sometimes called cusps, and they kind of look like a bird, like a seagull. They can look like that, where they're like concave down and then another concave down, or they could look like concave up and then another concave up. And then corners would be like absolute value functions. The domain of polynomial numbers, we talked about that earlier. Since there are no restrictions, the domain of polynomial functions is always going to be negative infinity to infinity. I want to look at power functions. Power functions are going to be f of x equals x to the n. So like y equals x squared, y equals x cubed, that kind of function. And I want to look at some patterns. If we have an even value of n, like y equals x squared, then that power, we can let that power increase hang on, I want to draw pretty far over here. Maybe even further down. We're going to do some sketching here. So, even value of n. We're going to look at some common points. We're going to look at domain and range. We're going to look at symmetry and whether it's an even or odd function. So those are all the things we're going to be investigating. So if I were to graph y equals x squared, that's one that we should all be familiar with. It has a vertex at 0, 0. And then I go over 1, up 1, over 2, up 4, over 3, up 9. I'm not going to sketch it in quite yet because I want to add some extra ordered pairs on here. So this is my y equals x squared. I want to add in like 1/2. If I put in 1/2, I'll label this point 1, 1. If I put in 1/2, then I would have to square 1/2 to get my output, which would be 1/4. So 1/2, 1/4 would be that ordered pair. So let me label that 1/2, 1/4. Because then I also want to look at y equals x to the 4th. So I'm ready to sketch, I think. Let's see, my next ordered pair would be 4, 16. I wonder if I can fit that. 10, 11, 12, 13, 14, 15, 16. No, I can. Okay. There we go. So there's my parabola, y equals x squared. And then y equals x to the 4th. For y equals x to the 4th, hang on, I'm looking for... y equals x to the 4th, we are going to put 0, 0, because 0 input gives me 0 output on y to the 4th. If I put 1 in for x, and I do 1 to the 4th, I get 1 out. If I put 2 in, 2 to the 4th would be 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2, 16. That's going to be way up here. If I put 3 in, I would get 2, 16, something big, 81. So that's not going to fit on here. On y equals x squared, we had 4, 16 was that order pair. What happens if I put in 1/2? So this guy's going to be y equals x to the 4th. If I put in 1/2, 1/2 times 1/2 is 1/4, times 1/2 is 1/8, times 1/2 is 1/16. So that's way down here. So 1/2, 1/16. So when I connect these dots, in here between -1 and 1, y equals x to the 4th is down lower than y equals x squared. Now that's a little hard to see, but it's down lower. It scoops down closer to the y-axis. And then after I go through the ordered pair 1, 1, I have to go all the way up to 2, 16. So that's going to be quite tall. Oops, kind of missed my point a little bit. That's okay. So here's a comparison of y equals x squared and y equals x to the 4th. What do they have in common? What points do they have in common? they both had that vertex at 0, 0, and they both went through 1, 1. So common points, 0, 0, and 1, 1. The domain for both is going to be negative infinity to infinity. The range goes from 0 to infinity. They both are reflections across the y-axis. So they have y-axis symmetry, which means they are even functions. What's happening between -1 and 1 is as the degree gets higher, then between x equals -1 and x equals 1, the graph gets flatter or closer to the x-axis. When x is smaller than -1 or bigger than 1, the graph gets steeper or closer to the y-axis. Let's see what happens if we have odd values of n. So that's going to be like y equals x cubed. So I kind of want this one to be tall as well. I'm going to aim for sort of the middle of the paper since I know that y equals x cubed has the, the two sides, one up here and one down here. So on y equals x cubed, remember that one has an ordered pair at 0, 0, 1, 1, -1, -1. Then if I go over 2, I go up 2, 3, 4, 5, 6, 7, 8. So 2, 8, 1, 1, 0, 0, and then -2, -8. Now let's do that same thing again with 1/2. If I choose 1/2, so this is y equals x cubed. If I choose 1/2, then I would have to do 1/2 times 1/2, which would be 1/4 times 1/2, which would be 1/8. So 1/2, 1/8, pretty far down there. And then I'd have another one here. So this graph sort of looks like a parabola on this side and then an upside down parabola on that side. There's my y equals x cubed. Now my next odd value would be x to the 5th. So we're going to try y equals x to the 5th and see what ordered pairs we can come up with there. So 0 to the 5th would be still 0. 1 to the 5th would be 1. 2 to the 5th would be 32. So like that's super way up here. Like it's not anywhere on my graph. I'm just going to kind of go up here and label 2, 32. Then what happens at 1/2? At 1/2, I would have 1 to the 5th over 2 to the 5th. So 1 over 32. That is a super, super tiny number. So really, really close to the axis. So this one is going to be even harder to see than the even one. What's happening is the graph is going to be below or closer to the x-axis in between -1 and 1. And then it gets to be, really super steep after 1. Because it has to go down and hit like 232 and -2, -32. So again, we can see closer to the x-axis between -1 and 1, and closer to the y-axis between when x is bigger than 1 and smaller than -1. So this is going to apply to both even and odd. So with an odd value of n, what are our common points? Okay. Common points. We had 0, 0, 1, 1, and then we also had -1, -1 over here. Let's see. What's our domain? Domain would be -infinity, infinity on both. And the range this time, bottom to top, is going to be also -infinity to infinity. Symmetry. This one, if I rotate my graph 180 degrees, it should look exactly the same as it did before. So that has origin symmetry, which means they are both odd functions. So keep in mind that these guidelines will apply to a power function, not a function that then has other terms added onto it. But that same situation will hold, that in between -1 and 1, the graph is closer to the x-axis as the degree gets higher, and outside of -1 and 1, the graph gets closer to the y-axis as the degree gets higher.